Hi everyone, I'm Julius von Kügelgen and I'm presenting our work Semi-supervised learning, causality, and the conditional cluster assumption. This is joint work with Alexander May and Marco Loog from TU Delft and Bernhard Schölkopf from the Max Planck Institute for Intelligent Systems in Tübingen. We consider the setting of semi-supervised learning where we are given a small labeled IID sample of x and y from some joint distribution, as well as additionally a typically large unlabeled sample from P of x. The goal of semi-supervised learning is then generally to improve the estimate of the conditional P of y given x from additional information about the marginal P of x. In order to do this, we need to link these two distributions with some additional assumptions. The two most common ones are the cluster assumption, which posits that points in the same cluster of P of x have the same label y, and the low density separation assumption, which states that class boundaries of P of y given x lie in an area where P of x is small. However, we might ask ourselves when we can reasonably expect two distributions to share information in the first place, which can be leveraged for semi-supervised learning. For this, we take a causal perspective here, and assuming no hidden confounding, first factorize the joint distribution over its underlying acyclic causal graph G. The principle of independent causal mechanisms then postulates that this causal generative process is composed of independent and autonomous modules that do not inform or influence each other. Here, the notion of independence is not that of statistical independence between random variables, but of algorithmic independence between distributions as objects. Intuitively, we can understand this as calling two distributions independent if encoding them jointly does not admit a shorter description than encoding them separately, meaning that there's no shared information which could be compressed. Very importantly, this independence is generally violated in the backwards or non-causal direction, as illustrated here for the bivariate case of x causing y with some deterministic invertible nonlinear mechanism f. If we assume that P of x and the mechanism f, or more generally P of y given x, are chosen independently of each other, then we find that P of y typically has a large density where f has a small slope, and therefore shares some information with the inverse conditional f inverse, or more generally P of x given y. This idea has been applied to the setting of semi-supervised learning by Schölkopf et al., who consider this case of causal learning, where the distribution of the causal features P of xc and P of y given xc are independent mechanisms which do not share information, and semi-supervised learning should therefore be impossible in this setting. Conversely, in the anti-causal learning setting, such independence is between P of y and the conditional of effect features xe given y, but P of xe and the conditional of y given these effect features are possibly dependent and share information, as we saw previously, and semi-supervised learning is therefore, at least in principle, possible in this setting. In this work, we ask what happens if we have both cause and effect features of a target y, such as in a medical data example, where y constitutes a disease or diagnosis. Causal features include, for example, the age, sex, diet, or genetics of a patient, and effect features are clinical symptoms, test results, and so on. Similar to the causal learning setting, we find that, again, the distribution of causal features contains no useful additional information about P of y given xc or P of xe given xc and y, since these are independent mechanisms. And therefore, this distribution of causal features is not helpful for improving the target quantity of the y given all the other features. This leaves us with the distribution of the label and effect features given the causal features, which we can factorize in two different ways. The first factorization is a causal one, so the two factors on the right-hand side are independent mechanisms. But in the second non-causal factorization, we find that these two factors, the distribution of effect features given causal features and the target conditional of interest, may share some information. We summarize this in our main insight, namely that the distribution of effect features given causal features contains all the relevant information provided by additional unlabeled data about the target conditional of interest. Semi-supervised learning in this setting of causal and effect features should therefore aim at linking these two conditional distributions with some additional assumptions. We note that this contains previous results as special cases and therefore generalizes the understanding. In the causal setting, where we have no effect features, this conditional becomes meaningless and semi-supervised learning thereby impossible, whereas in the anti-causal setting, with no causal features, it reduces simply to the result of semi-supervised learning being possible in the anti-causal direction. In order to develop specific algorithms, we need to make some more concrete assumptions to link these two conditionals. And to this end, we propose the conditional cluster assumption, namely that points in the same cluster of the conditional of effect features given causal features share the same label y. We should think here of clustering in the space of functions mapping causes to effects, which arise from different choices of the noise variable NE in an underlying SCM. For example, in the case of an additive noise model with unimodal noise, we get two clusters as shown here on the right, corresponding to the two conditionals of interest. Note that large margin-based methods or clustering approaches would not recognize this kind of asymmetric structure and therefore classify simply by thresholding the causal features at xc equals 0, thereby achieving a large error in this particular example. We propose two algorithms, the first one being a semi-generative model, where the idea is to fit a generative model only to the informative part of the distribution, meaning conditioning on the causal features and only modeling the distribution of y and xe. This requires assuming a particular parametric form, and the approach then proceeds by maximizing the conditional likelihood of both the labeled and unlabeled data, for example, using an expectation maximization procedure. The second approach, termed conditional self-learning, relies on the idea of using regression errors for a self-learning approach. It assumes a zero mean additive noise model, and the approach proceeds by first initializing these two regressors, F0 and F1, from labeled data, then getting predictions for all the unlabeled data points, labeling that point with the smallest prediction error, and then retraining the two regressors and repeating this procedure until all points have been labeled. We performed some experiments on 3 synthetic and 2 real-world medical data sets with cause and effect features. And just to highlight some results, we find that the semi-generative model performs well on the synthetic data sets where the parametric form is known, but not so much on one of the real-world data sets. While the conditional self-learning is the only method that outperforms the purely supervised logistic regression baseline on all 5 data sets, thereby achieving semi-supervised learning. Generally, our methods perform slightly better than more traditional semi-supervised learning baselines, such as transductive SVMs or label propagation. So in summary, the causal structure underlying a problem has important implications for the possibility of semi-supervised learning and specific approaches to how this should be done. When learning with both causes and effects of a target variable, all the additional information is contained in the conditional of effect features given causal features. And we can use this insight to refine standard semi-supervised learning assumptions to instead link these two conditional distributions as proposed, for example, in the conditional cluster assumption. Thank you very much.